Someday you'll be able to control batteries.
I hope not.
Something to aspire to.
Any administrative role, I'm fine with that.
All right, let's settle down. It started a minute early. Okay, so we have three nice talks in the second half of the closing session here, and we're going to start with Patrick. Emulating nuclear matter.
I
Do it.
All right. So it's almost like the organizers know what they're doing because the talks before me covered all of my background. So we'll see if I actually need 20 minutes. Hopefully everybody was studying and taking notes over Pablo and Christian's talks. If not. All right, so we're gonna start at the end and then we'll get back to this. But this is the propaganda, right? So we're gonna do some emulation of some high fidelity stuff. That's great. And of course, the goal of emulation is to make something cheaper. Cheaper could be faster, could mean literally cheaper in terms of US dollars, or it could be being able to do uncertainty quantification, which is still just I was able to evaluate more things and therefore it was faster, so I could do uncertainty quantification. The one that we usually didn't think of until maybe a year ago was memory. I actually looked up what the cost of this in a server is right now. It's literally a down payment on a house. Like that's not an expression. It was literally $30,000. So it's also nice that we can make these things very, very small, not just fast. So this is what we're going to work towards. But we got to figure out what we're doing first. So nuclear matter and the, in parentheses, nuclear equation of state. I'm not going to cover this too in depth, but right. So we have this idea of a neutron star, or kind of the bulk of the neutron star, and it's just a bunch of nucleons that interact. And the nuclear equation of state is okay. If we have that system, how do things like the pressure and the energy interact in terms of what's their relation, and maybe other observables like the incompressibility. How does temperature play into this? Of course, here we won't be dealing with temperature because we never deal with temperature except for when we do. And this is a really important part of nuclear physics. If you need convincing of this, then I'm not the one to do it. But if we can tie together the smallest things, well, not quite the smallest things, very small things, atomic nuclei, and some of the larger or more massive things, neutron stars, that we can actually observe quite easily, that would be great, and work towards a more unified theory of everything. So I stole this figure. But this is the interaction that is, well, an interaction, I should say, a good interaction that people are fond of. And it just comes from expanding chiral effective field theory. So Christian showed these exact same diagrams in a better figure that I'm sure he didn't steal from someone else's paper. And we have these parameters that actually tell us about this interaction. So these low energy constants. He had brought this up with these CD and CE, the three nucleon LECs, but then there's also the D2, E2, and F2, these new ones that were identified as potentially being more important than previously thought. So this is the interaction we're working with, and oh look, I already said this. So yes, this is what Christian had brought up recently. These forces that were thought to be high order were shown that maybe their contributions are actually as important as some much lower order terms. And so it'd be nice if we could maybe play around with this and see, oh, can we see this from instead of a first principles chiral effective field theory expansion, can we see this from the astronomical observables and kind of work into the middle, figure out if it's all consistent. So I don't have to convince people here that IMSRG is pretty cool, powerful. I think that's maybe the more common ab initio solver in this room. Could be wrong there. But it's certainly very powerful in terms of being able to reach deep into the nuclear turf for heavy nuclei, and also being able to do infinite nuclear matter. It's not perturbative, it's neat, but it is expensive. That's okay, because expensive hopefully should translate to useful and accurate. Here's another figure I stole. I told Heike that I stole this, and he didn't say I wasn't allowed to, but I also didn't ask permission. So this is the idea. I'm not going to spend too much time covering the high fidelity stuff. Suffice it to say, we trust the high fidelity results. That's not to say they're perfect, but we trust them. Okay, so here's the two goals of this work. Can we build an emulator for nuclear matter calculations? And that's really going to be the output here. We're going to make this emulator. and show that it's possible, it's very good, and do UQ with it and UQ on the emulator itself. And then we're gonna just try playing around with it, show an application of the emulator. It will be useful for much more later on, future work, job security, yada yada. But for now, let's just play around with this new 3-nucleon force governed for these new 3-nucleon forces that aren't new, but now kind of new and are governed by the quark masses or related to the quark masses. All right, so we always have to choose an emulator architecture. Pablo's talk was literally the last talk, so if you don't remember that, I don't know. I can't go over the whole thing again. It's great because you got 20 minutes to do something I was going to have to do in 2 minutes. But all we care about is getting the ground state energy of this Hamiltonian as a function of all the parameters we'll end up caring about. And IMSO G, for all its power, really just doesn't have good access to vector data, eigenvectors specifically. And so doing kind of a traditional Petrov-Galerkin explicit reduced basis method is off the table here. Even if we had access to that information, it would be far too expensive, not really worth it. Yep, I said this. This is great. And kind of an interesting part here is that we're not just interested in going from these LECs directly to the energy. We want to be able to get the equation of state relations out of this. So as we change the density in the Hamiltonian, which is a bit different than changing an LEC, a lot different than changing an LEC, will the energy respond correctly? And then can we start taking derivatives of this relation to get all sorts of interesting things like the saturation point, which is where you get the absolute minimum energy as a function of density for symmetric nuclear matter, or at least for non-pure neutron matter. All right, so this is the very simple. That's right. Okay, this is a very simple overview of kind of what's happening here. You have some Hamiltonian as a function of these parameters C. It doesn't matter what these C's are, and it looks affine. And then we could do the standard approach, which is just find a projector P and its quote unquote inverse P dagger, and just project all of these operators down and make a reduced order model that way. Now we don't have P, and so this is what Pablo is talking about, or at least this is a slight subset of what Pablo is talking about. These implicit methods. So we say, okay, I don't have P, I don't have H sub I either, so I can't do this, but I know it should look like this. And I have all of these properties of H sub I, like its Hermitian, and maybe I know something about its spectrum, so I know maybe the extremal eigenvalues, things like that. And then I can specify, okay, I want to impose P, some properties on P. So again, I can't make P, but I can say, okay, I want it to be orthogonal. I want it to be an orthogonal projection. Or, oh, I want it to be norm preserving, but it doesn't have to be orthogonal. All of these things. And with, these ideas, nothing really concrete, right? So ideas of what H sub I should be, what P should be, I can say, okay, then I'm just going to call that this underlined H sub I, and I'm going to learn that from the data. This is the implicit reduced basis method. Sorry, again, it's a slight subset. There are a larger class of implicit methods, but here we're restricted. And this is equivalently called PMMs. It is a very slight subset of these implicit reduced basis methods. So it's not just eigenvalue emulators. It is, you take whatever equation you have, you imagine what the explicit RBM would look like, what Petrov-Galerkin would look like. You specify the properties of both the high fidelity operators and the projection operators that you want, and you fit directly to your data. There's some other massaging you can do, and nonlinearities are handled slightly differently than in explicit RBMs. Read my thesis in a month or don't. And this, so this is what I just said. Nothing is sacred about the form of the Hamiltonian. So it didn't have to be an affine eigenproblem. We could have done this with anything you can imagine a full order model for. Nonlinear, linear, doesn't matter. The process is almost exactly the same. All right, so we chose an emulator. Now, again, I say designing in these giant air quotes because we should have no choice over what the emulator looks like. It should be whatever the high fidelity model is, our best guess for it if we don't know it exactly. That is going to be the form of the emulator. The less choices we make, the less likely we are to make a mistake. So Pablo mentioned this trade-off between, you can take a black box method that's always the same and apply it, and you can take a maximally intrusive approach where you spend months figuring out all of the intricacies of the model, and that's going to give you maybe a better emulator, but it took you so much longer. I am of the opinion that we should always do our best. If that takes 2 years, that takes 2 years, and that's certainly a trade-off that I'm on one side of. And so Christian can definitely account for this. There's many meetings going back and forth, helping me understand what in the world is IMSRG trying to do, not necessarily what it does specifically, but maybe its philosophy of what it's predicting. And so we can make the onsets, if you will, for our reduced order model correct. And so in this case, we have this free space Hamiltonian. So this is just the interaction, basically. And it's this chiral effective field theory expansion. So as a function of the chiral order nu, we have the leading order and then the next to leading order, which involves these LECs, C sub I, and then we have the next leading order, and so on up until we don't want to do it anymore. We stop it in 3LO in this work. So relatively simple form. Everything's affine so far, but this is just the free space Hamilton. Right? IM in IMSRG is in medium. So we're going to go to the in medium. Oh, okay. I could also write it like this. It's a little more compact. Doesn't change anything. So we go to in medium. In medium just, okay, Heiko, I'm sorry. I'm going to get this wrong, but I'm going to try my best. In medium means instead of solving the free space Hamiltonian, taking, this answer and then plugging in things like your specific choice of basis, your specific density, your specific nuclear matter configuration. So is it pure neutrons or symmetric or asymmetric? You're going to do that first and then you'll solve it. And so all of that equates to a basis transformation. Now, whether or not this happens in practice, fine. Philosophically, it's just a basis transformation, which I can write like this, where I have these semi-unitary, rectangular unitary projections that depend on all of the things that define this in medium, the medium, if you will. And so these are things like the computational parameters. So in sub S is like the number of closed shells that I use when taking a finite number of single particle basis states and writing this interaction in that finite space. Things like the matter configuration. So like I said, pure neutron matter versus symmetric nuclear matter. This is the proton fraction, and then the density n. And so that basis transformation, we don't know exactly the form of it, or at least I am not going to use the form of it even if I did know it, because it's very complicated. But we can say it's definitely a partial isometry or a basis projection that depends on those things. And so we can put the underline, which just means, okay, now I'm going to learn that from data science. But I want to get all of the dependents correct, or as correct as I can. I want to make sure that I'm not just learning a single U. I want to learn U as a function of these things. We'll come back to that. So just remember for now, I've omitted the dependence on these things. And so this isn't complete yet. It's still just imagining that blurry picture that Pablo had, intentionally blurry. I'm still in the blurry phase. And then we'll diagonalize this in the reduced basis, and we'll find a ground state energy. Christian, I'm sorry, I still used not instead of GS. I'll switch my notation to be correct someday. Okay, so that's our blurry picture of the IRBM, the PMM, the other 3-letter acronym, it doesn't matter. All right, now IMSRG, again, for all its fantastic, it's not exact, right? We would have to flow, for people familiar with IMSRG, out to infinity. We're not going to infinity. None of us are going to live that long. We're going to go to some finite S that's large enough to be good enough. And the dependence of the prediction on S is very difficult to nail down. I wouldn't have thought that when I started this. In fact, I didn't think that when I started this, and I now know that. So sometimes I'm wrong. Okay, sometimes. Now, thanks to people being smart, we at least have an idea that, okay, it should be some sort of decaying exponential. So x sub h here is just all of those Hamiltonian parameters. The flow is a numerical parameter for IMSRG. I guess it does have physical meaning. I'm sorry, Heiko. Scott's not here, so I don't have to apologize to him. No one tells Scott how I've butchered his child. So we know it's the exact, in theory, it's the exact actual ground state for that Hamiltonian with all those parameters, plus some decaying exponential corrections that each of the decaying exponentials depend on these Hamiltonian parameters. So again, I don't know what alpha, the actual form of alpha in terms of all of these Hamiltonian parameters are. I just know that it's positive, or rather strictly non-negative. And same thing with beta. So again, this is part of the blurry picture. I don't know what I'm going to use just yet for those things. Whoops. All right, so that's pretty much the picture. We have to iron out the problems of what in the world are alpha and beta's dependence on the Hamiltonian parameters, and if we go back, what in the world is this basis projection? What is its dependence on these things? Well, I said before, we really don't know, or at least I am not going to use that information even if I did know it. Instead, we're going to substitute some data-driven things. So we were doing all physics-based stuff, all basically an explicit RBM, imagining we had the ability to do that. And now we're going to put a little bit of almost pure machine learning in there, where I'm going to introduce universal functions. So you can imagine these are the output of a neural net, the output of polynomials that are sufficiently large with tunable weights and all this. And they depend on those parameters that I didn't know how my basis projection depended on. And if I do this weird math thing, which is just a matrix exponential of some Hermitian matrices that are summed together, I can guarantee that at least this part here, just going from the exponential, that if I have enough f's that are expressive enough, so big enough neural nets, if you wanted to imagine this in the neural net picture, that can represent any unitary matrix, right? As of any unitary matrix function as a function of these three variables. This is just the standard universal approximation theorem applied to unitary matrices. Now I need it to be a basis projection, so I take my unitary matrices and I truncate some of the columns. So that's just what this weird notation is. I'm going to take k columns. K has to be less than the size of the matrix itself. The idea is that this is a universal form for any possible partial isometry, rectangular unitary matrix, given sufficiently expressive f's. Now, getting a little bit in the weeds, I'm going to not use neural nets for f. Neural nets, again, powerful, but maybe too powerful and too jagged and all of these things. I'm going to use a very specific data-driven form of a PMM that we've crafted to be analytic and smooth and tunably smooth and all these things. It's going to help us later. The paper will maybe touch on this a little bit better. So now I actually do know how to project, how to make the RBM for you, because I've specified this form. I'm saying, okay, this is just some function, some scalar valued function. So I can, if I sandwich my projectors on either side, they move into the matrix exponential because it's analytic, or at least analytic where we care about. And so the trainable operators are just these, and we know how to do this. This is great. So this is the magic graph. I didn't have time to remove all the stuff I didn't talk about, but this is pure machine learning nonsense, all of the orange. So just ignore that. It's just data rescaling. But this bizarro graph is that reduced basis method. We take all of our inputs. So we have our chiral order, we have our LECs, we have our proton fraction, some numerical parameter, the density and the flow parameter. We construct the free space Hamiltonian. We use all of the things we need to use to come up with some data-driven form for these universal f functions, which can make our universal form of our basis transformation. We apply that basis transformation, we get the in medium form of the Hamiltonian. That can give us the ground state at infinite flow. Then we can add our finite flow corrections on top of that, and we get our final prediction. And all of this is in that reduced space. So all of these things are much, much smaller than the full size Hamiltonian. Now, again, Pablo had mentioned, doing all of this work takes time also. We can't just focus on the training time and the inference time. We have to focus on the human time, because that's much more finite. And I've done all of this work for you. There's a library here. Library is on GitHub. I didn't put the link here, but you can find it. Google parametric matrix models, GitHub. It's right there. You still have to do work, right? Because in my opinion, I don't think you can prove this, but the best emulator is the one that includes as much of the physics information as possible. Not just applying a neural net as a black box, not just applying an eigenvalue emulator as a black box, but going through this process we just did. But all of the infrastructure, connecting these things, training these things, very carefully handling all sorts of JAX optimizations, running it on GPUs. Nobody here wants, well, I wanted to deal with it, but I doubt most people here wanted to deal with that. So that's all done for you. And then each of these boxes are just a class. You instantiate a class and you say, okay, this is the class that does, the exponential function. This is the class that does an affine Hermitian matrix. And you just connect them all together. I don't have a graphics interface, but it could have one. Somebody else should do that. I don't really want to work on that anymore. But so I think Pablo and I can have our cake and eat it too. We can do the most complicated, hardest thing, as long as somebody in this case me, does all of this upfront work to take away all of the general things and put it in a library, and people use it hopefully, and it has good documentation, hopefully has good documentation, then we can do the thing that would take 2, 3, 4 years, not in 2, 3, or 4 years. Christian, how long have we been working on this? 6 months? A year?
Something like this.
So it's better than 4 years. You're gonna get it down farther. So that's great. So this is our emulator picture. This is for the machine learning nerds out here. Because we collect all of our data. So we run IMSRG, we get a whole bunch of samples. So this top one is for symmetric nuclear matter, bottom one, pure neutron matter. And now we want to split our data into training, validation, calibration, we'll cover that later, and testing data. And since we want the model to be good at extrapolation, we specifically restricted its information in that regime because we want to be able to test in pure extrapolation. If we had data in that regime, then it's not extrapolating, it's just reproducing data. So we want to be able to show that it's doing good. Afterwards, people can ask me about this. There's some, like I didn't define what this means, and it's some IMSRG stuff. So afterwards, if you have more questions about this, we can talk about it. Okay, so we have the emulator. I'll get to UQ later. How well does it just do? Can I reproduce my, well, actually, can I fit my testing data, the data I didn't see before? So these are the classic plots. If it was perfect, it would be exactly on the diagonal, and it basically is. And I've had to use the 95% confidence interval because I used the standard 1 sigma, it's almost too small to see. So that's a hint that this is going well. And so for both N2 and N3LO, this looks very good in both the symmetric and pure neutron matter regimes. That's great. So like I said, we built this emulator and the uses for it are much more than this, but for now, let's just play with this new F2 interaction and see, does it actually do anything? Does it change how our nuclear properties, our saturation properties manifest? And it does. So it's a function of the saturation density and the saturation energy. If we don't include this F2 moderated interaction, you get this band, which doesn't really cover much of where the empirical saturation point should be. Technically, it is consistent for some of these things, but not, we would like to be able to tune this interaction to be consistent, more consistent, if you will. If we add F2 in here, the whole band just widens. And there are many reasonable configurations that do indeed reproduce the known empirical points. So that's great. So kind of an example use case for the simulator. All right. So Christian brought up UQ. Pablo brought up UQ. I hope everybody probably brought up UQ. So there's a difference between UQ as like, we have the emulator, it can run fast, so we can do the UQ on the high fidelity model through this surrogate. This is, I want to do UQ on my emulator as accurately and hopefully efficiently as possible. That way, when we do that second, or that original UQ where we're just running over and over very fast, we can include the emulator error in. So I'm going to use conformal predictions, more specifically split conformal predictions. My first degree was in math, and so I really like being overly rigorous about things at the dismay of everyone around me. And so that's why I've chosen this. But it's also, compared to the thing that we're usually doing, where you have a big ensemble of models that you train them and then you do statistics over their outputs, this is much more efficient. And it's also more accurate in terms of, I'm very confident in my uncertainty bounds, which is great. So the idea is basically we have that calibration set that I mentioned before, and through only the assumption of the exchangeability of data, right? Every data point is equivalent to every other data point in terms of importance or meaning and whatnot. We're going to do statistics on that calibration set, and then we're going to translate those statistics to unseen data. How do we do that? Well, we're going to cover this kind of broadly. We have a score function, which is our residual, our error, weighted by the uncertainty heuristic. Now, the uncertainty heuristic is the only thing that matters. It doesn't need to actually be the uncertainty. All it needs to do is order our points such that points that are more uncertain have a larger uncertainty heuristic, and points that are less uncertain, or rather lower error specifically, have a smaller uncertainty heuristic. That relation doesn't need to be any more specific than greater than. And the output of this is going to be prediction set. So instead of, oh, I give you give me the parameters I plugged in my emulator and you get a point back, now you get an interval with some significance level, alpha, or confidence level. I can tell you, oh, here's the interval, there's a 95% chance it lands in, or rather 95% of the time your point lands in. And this is guaranteed coverage, which is amazing. So I actually am going to skip this. If people want the details of how I very meticulously designed an uncertainty heuristic that works for any model that's designed on implicit RBM's parametric matrix models specifically that are nice and affine and continuous, and we can take derivatives. We can talk later. This was a lot of effort, very carefully done. But let's validate this approach. So if I come, or you come to me, you give me some parameters, and you say, okay, with confidence level blank, give me an interval, and then you do this a million times, and you see how often was the point actually in that interval. Okay. So it's kind of like the Weatherman problem of, I say there's a 20% chance of rain on Saturday. How often is there actually rain on Saturday? And so in the best case scenario, this is a perfect line just like the other one. And it basically is. So for the test set, which is the only one that matters, above 20%, the maximum over coverage, so where I'm more pessimistic than I should be, is less than 2.5%. Which is pretty good. Now, the part that really matters is the under coverage. How often am I overconfident? Less than 0.35%. So this is, I wouldn't trust any other model more than this, basically. This is great. And so when you come to me and you say, okay, I need the answer with an 80% confidence level, I'm giving you an 80% level. Basically, exactly. And so then I can just hand everything off to the real physicists. The whole model fits in 700 kilobytes. My library is online, so Kong can just take the attachment from my email. He can download the library and run it and do all of the Bayesian Buckeye collaboration, work backwards and figure out what are the best LECs. This is not part of what I do. So I'm not going to cover it, but we can talk later if you're a physicist, unlike me, and are interested in these things. And then I said the beginning was the end and the end is the beginning. So we're back to the beginning. When you quantify this, it actually works very well in terms of the propaganda of how much faster it is. But like I said, we have the UQ to back up how accurate it is as well, or trustworthy rather. All right, I'm done. Cool.
Patrick, we are open for questions.
Go, Kyle.
Go, Kyle and Jordan.
Mine might be quick. Have you put any thought into so you put together the package, put any thought into some sort of schema or composable format so that, or specifications, so you can easily share an emulator form between people, or?
I mean, beyond, pip install my package and then
Python script.
dot from file, here's the model file. No, but what more could you want? I don't know.
Thinking a spec could be nice to basically design the emulator in a JSON format.
Oh, so I've mentioned that this could have easily been done with UX. I'm not a front-end developer. Have you heard of, I think, Comfy UI for image? Yeah. It would look exactly like that. Actually, that graph that I showed that is the model, there's nothing stopping anyone from turning an editor that makes that graph directly into the code. But I'm tapped out when it comes to front end. Yeah, there's no, yeah.
Okay.
It could be done. It should be done. Hopefully it will be done.
Pablo, you had a question or comment?
Yeah, fantastic. I really like it, and particularly like the diagram. It's very useful for later changing it.
I'm glad it flashes when I switch.
Okay. Yeah, I love diagrams like that. But very good. My question is about the conformal thing for you. You explained it, but I think I got lost in the simplest term possible because I would like to start playing with that. What exactly do I need to make that work? If I have an emulator or any prediction?
Yeah, so you need some sort of uncertainty heuristic. So unfortunately, the reason why you don't see this in literature is because the thing that people usually do is they train another neural net to predict the error for their neural net. If that worked, you would just subtract off the error and have a perfect, that never works. So you get a really, really bad heuristic, which means that your error bars are always over predicting, you're always pessimistic. And so you need to come up with a good thing for that. That's the hardest part. That's why I'm very proud to have done that for any PMM that you can make in my library. The second thing you need is the data that you already had. You just carve out a calibration set that needs to be statistically similar to your expected unseen testing data. And that's it. So I forgot to put this on the slide. If you look up a gentle introduction to conformal predictions, you basically only need the first 10 pages.
But what is the mapping that takes from heuristic that you calibrate? You calibrate this thing. What is the mapping? What is the functional form that you're using?
You take this this ordering, right, from the uncertainty heuristic, actually from the score functions more specifically, and you take quantiles of that are based on this significance level. the quantiles tell you this correction factor Q that you apply to your uncertainty heuristic directly. And that goes from being this heuristic to an actual uncertainty interval. So like I said, a gentle introduction to conformal predictions will cover this exactly. It's only a couple more equations, but I put enough equations in this talk.
Thank you so much.
I think I'm out of time.
Yeah. Okay, let's thank Patrick again. Lauren is up. Okay. Sharing a computer.
So she's gonna.
You want to run from your computer?
Yeah, she's gonna share.
Oh, okay, sure. Okay.
Free to, and you can put your.
Yeah. So I'll flash 5 when you're at the 20-minute mark.
Okay, sounds good.
Yes.
Oh,
Okay,
yeah.
so surrogate models for linear response.
Okay,
Lauren?
hi, I'm Lauren. I'm an undergrad here working with all of my advisors on today, Pablo, Kyle, and Vitek. And today I'll be,
You, please speak.
Oh, yeah.
um,
Really?
Double click on the,
Double click on the,
like in the slide area. Should full screen. Right?
okay.
Hey. Thank you.
okay. So now I'll be telling you guys about our surrogate models that we constructed for linear response theory and some extensions that we've made for you guys' usage. So before I go on, that QR code is going to take you to a site with all of the resources that we've compiled for our project. It contains the paper and it also contains a link to the repository. So if you guys want to look ahead, or I sometimes talk slow, so if I get bored, you guys can also look ahead. So just put a bit of formalism to what we built the tool for. Linear response theory is a way to predict how a system reacts to when you gently disturb it. So starting with a known reference state, then you apply a weak external influence and assume the change in that system is proportional to that influence. The resulting physical observable from the theory is naturally called the response function, which I'll expand on a bit more later. So our chosen system's application of linear response theory is QRPA because our group focuses on DFT methods. So the QRPA, or the quasi-particle random phase approximation, essentially describes small amplitude oscillations around the mean field description. It's built on top of a HSB or an RFB or RHB ground state reference, and subjected to a weak external field that depends on your excitation energy. And there is a linear response formulation of this, but just for convenience, and this is going to be the form that I referenced throughout the talk. So this is the matrix formulation of the QRPA. So just a little bit more about how you extract the response function that I mentioned earlier. You start off with your matrix QRPA formulation, and times Zn equals your energy plus your Zn. So this is an eigenvalue problem, and your Zn here is your QRPA mode eigenmodes, and your omega n is the excitation energy of that mode. So each solution gives one possible vibration of the nucleus corresponding between your mode and your energy. And then the external field that you apply decides how visible that mode is. So the strength of mode n is expressed by a squared dot product between your external field vector and your eigenmode, and you get your strength function as a representation of all of those factors. So if you look on the plot here, that strength B, or the omega n, determines where your poles are going to be placed at, and that B determines the strength of your that response. And for our case, when we're trying to apply this, when we're trying to do this calculation for nuclei, For spherical nuclei, the matrix size goes up into the few thousand size matrix. For like a deformed case, it goes up into the 10 to the 5, 6 dimension. So obviously, it's just from that alone, there's a computational plug in your algorithm. And this plot right here is showing a system that we used for our paper, but for our cases, we vary 2 parameters, but this is the response from just varying 1 parameter. And you can see even just from that 1 parameter, the strength has a lot of variance, not just left and right, but also in orders of magnitude. So there's not an obvious way that you can choose the coordinates that you want to reduce your equations for. But keeping that in mind, I just want to kind of show a few necessities for solving this problem. Just this week alone, or since coincidentally there was nuclei meeting earlier this week, I just compiled a few use cases and developments that's been made in both the nuclear physics perspective, but also the numerical perspective, and also the need for these calculations for example, for like global studies here on the top right. This plot on the bottom right, I actually liked really a lot because this is from the perspective of a applied mathematician, and they're putting in all this work to reduce the time that it takes for each calculation for this response. But even with these high fidelity methods, there still is computation time is still in the order of hours. So I want to kind of support this this problem from a complementary approach. So coming back to that problem child, we need to think of a way to find coordinates that can really best represent the strength function. And we all of us kind of banged our heads on the walls a bit, but I think the key motivation that we had was maybe that observable response doesn't need to depend on that full giant matrix. Maybe the physically relevant response can be represented by a much smaller effective matrix. And so then our aha moment was, okay, so then what if we can kind of get away with just a few effective Lorentzians? So then it's very clear what our right coordinates is going to be. So instead of constructing that full QRPA matrix, from the EDF and the residual interaction, we can approximate that full strength function with just a much smaller number of Lorentzians, and so essentially you're solving a much smaller reduced matrix, and then fit the newly reduced matrix to your data. So the simulator essentially reproduces that strength function as like an intermediate latent object. And analogously to our full order matrix, your reduced coordinates are just your Lorentzian locations, the amplitudes for each of those poles, and then the effective width that you can see the analogous form. So just kind of taking a step back from the smaller parts of the calculation, just to give you a summary, the emulator isn't directly learning the full function that's dependent on the energy as a black box map, and that's actually not the exact emulation approach. That's the high fidelity calculation. But anyway, so our emulator is essentially mimicking the spectral representation of the QRPA response. And we actually constructed a second emulator for our paper as well. That actually kind of just does that as an immediate black box from your input parameters to your output observable. And so I guess from now I'll just call them emulator 1 being the emulator with the structural input, and emulator 2 being the one that we just bypassed. But anyway, emulator 2 essentially bypasses that intermediate strength function that I said, and it directly connects the controlling parameters to your observables. We used PMMs to train that emulation. And we obtained the eigenvalues of the obtained matrix and used the selected target observable to yield the, yeah. So anyway, so emulator 2 isn't exactly, it's not emulating the QRPA response in the most physical sense. So it's more data-driven response, data-driven approach, but thanks to the features of PMM, you can make it matrix-based and but not the same QRPA response-based in the same physical way. So I guess I wanted to make another note on the emulation approach here. When I was registering for Streamline, the first thing I noticed was, the core focus areas of Streamline, and there's all these terms of like, reducing speed and in optimizing your algorithms, but also maintaining accuracy with our tools and making smart modeling choices and predicting correlations and phenomena and etc. And Christian touched on this topic as well, and Patrick as well in two different ways, but I think I think it's always a good approach to take a step back from your entire computational pipeline and take a look at the original model, see how much of that physical model you can retain and keep, because that maintains the rigor of your calculation, and also just taking a much scoped approach from just looking at the issue of how can I solve this problem. It's also an effective way that you can systematically diagnose where the errors in your predictions are coming from, and because you can isolate where the machine learning is actually going into that pipeline. And yeah, and I guess also in the long term thought of Bayesian UQ, and when all of these uncertainties are piling up in each part of the computational pipeline, I think those uncertainties really matter in doing high precision physics, not just for experiment, but also for theory as well. So this is actually emulator 1. You can see just the exact parts that we incorporated the machine learning into our approach. So with that philosophy in mind, these are some results. The left plot on here is with all of our data points. The shaded region here is the training, and the training region here is in sub% error from 0.01 to 0.2%. Everything outside the shaded region is the testing region, and it's around 1% at most, 2% in error. And this plot on the right is just 3 chosen spectra from the grid of points. 2 of them are in the testing, and 1 of them is in the training. You can see that the emulator is able to capture that behavior really well. And I don't know if you remember from way early on when I showed the high fidelity version of this plot, this thing spans orders of magnitude. So just a note on the significance of that. And to give you kind of an idea of how fast it is, this is a website that our group worked on launching. The emulator's super fast. Wait, no. Sorry, I stopped sharing. Super fast. If you clicked on that QR code earlier, well, not clicked on it, but if you went to that QR code earlier on, it would have taken you to the site, which is just a basic description, but it also contains okay, I don't know. Reload. Yeah, it shows you the variation with parameters, so you can play around with this real time because it's so fast. I guess going back, stop sharing. Okay. So yeah, it doesn't need a server. It can run locally on your computer. So now you guys can do something that takes months on a HPC on your laptop. So just kind of coming back to the 2 approaches that I mentioned earlier. Just a reminder, emulator 1 is emulating that spectral representation of the QRPA. Emulator 2 doesn't emulate the response function itself. It just emulates it just emulates your final observable through a learned machine learning. And the note the note I want to say with this plot, this is a violin plot of um your comparing emulator 1 and emulator 2. You can see that emulator 2 on the right in red is really susceptible to overfitting. This red part, which was in the darker, is in the training, but this thing can just go down as much more as you need to, which shows signs of overfitting. And you can see in the emulator 1 case, the error between the error cluster between your training and testing region is a lot more correlated and clustered. So yeah, just better test of reliability and how that distance shifts in the testing region. This is another plot. So the blue again is the emulator 1. Red is again the emulator 2. You can see that the errors of the emulator 1 is a lot more correlated. The errors in emulator 2 is a lot higher. This one, the diamond is or no, this square one is the one in the testing region. You can see how it completely shoots upwards. So compared to the error. So another note on that. And I think somebody had mentioned yesterday, I don't recognize who it was, but I think the question was something along the lines of like, if it's going to take you this long to construct the emulator, is it really worth it to do that, then just run your high fidelity calculation? And I think yes, I think it's worth it. The framework is out there in the literature, but also I just showed a plot. This is a plot of or not a plot, table of comparing the hyperparameters that we're tuning for our emulators. This is for two sizes of the reduced matrix, and the hyperparameter count for emulator 1 is a little bit higher than emulator 2, but if you think about it with a bit of nuance, emulator 1 is using these hyperparameters to tune the Lorentzian pole, the strength of that Lorentzian, and the width as well. So there's three factors that you need to take into account for these hyperparameters, and for emulator 1, it's just or emulator 2, it's just predicting that final scalar observable. So taking that into account, I think that's a very clear sign that you can end up using less training data too. And then I took a little bit more scope back. I think the original question was actually this, do I have a lot of projects going on. It's going to take me a while to learn the framework and apply to construct the emulator. So I guess I don't really have a good solution for you. If you're interested in the emulator framework, you can learn more, but to reduce the work for you, I built a software package for it. So now you don't need, you can put in the same amount of work for constructing an emulator 1 or constructing an emulator 2. And it supports, I wrote ND spectral emulation, but obviously it's not a trivial problem to just shoot up in the parameter space that easily. And I put in a few test case examples that are outside of nuclear QRPA that I'll show in the next slide. But I welcome you guys to play around with the software package, play around with the emulator. If you guys don't want to touch this software package at all, you can just email me and I'll do the work for you. Yeah. So yeah, and if you guys have any feedback, you're always welcome to give all the feedback, nice or harsh and everything. And as I did promise, these are some usage examples that we've had since building the emulator, building the package. This one on the left is from earlier this week by Yukiya during Nuclei, and he's doing a Bayesian calibration and used the emulator for his case. This case on the right is from the atomic world. It's a hydrogen 2 squeezing with the two parameters, the angle and the momenta. So yeah, here's an example outside of nuclear, and the spectral on the bottom is another example within nuclear, but with a completely different underlying linear response method. So lots of use cases, lots of different sources. So any response functions that you guys are able to contribute will contribute greatly in the software package. And with that, thank you for your attention.
Very much. Patrick, you want to read us off?
I think that you can slide with a table of parameters of two different.
Yeah.
I want to make sure I can miss something. You said these were learned parameters, but you called them hyperparameters.
Oh, so hyperparameter. Sorry, I mix up terms, but
Yeah, they're the learned parameters of.
So they're not,
Yeah.
not hyperparameters.
okay. Yeah.
Hyperparameters are.
Yeah. Yeah. Okay.
I just want to make sure I didn't.
Yeah. Sorry, I mix up terms.
You're overfitting things here about validation, or rather, sorry, testing data or performance optimization. Both of them, Belieu one and Belieu two, more than an order of magnitude difference in certain regimes. Is this what kind of maybe validation or early stopping would you use with both models? But I assume they were trained very similarly using some gradient descent. Do you have a validation set that's statistically similar to your testing set? Would you use loss function based early stopping?
Yeah, so we did make a couple couple choices in the construction to take those into account. One that comes to mind is like if there is a limit in the not too much variation in the relative change in the loss, then we did put in a cut to cut the training. The other one was in the cost function. It's not just like for the strength function, for example, like we did incorporate the strength loss as along with the observable loss. So yeah, I don't know if that answers your question. I heard it partially. Okay.
Good questions. Can I just clarify? So your initial use case was this discretized QRPA, right? You just got
Yeah.
And your actual physical output is a continuous response function.
Yeah. So
So from that point of view, you actually didn't care where it came from,
yeah.
and that's why you were saying it's just general and stuff.
Yeah.
It's just the model is actually a set of Lorentzians.
Yeah. And I think that's why it's able to generalize so well to other use cases as well. I think actually in Ante's calculation, Ante, clarify if this is wrong. We did a spherical case and we did a deformed case. I think the deformed case is from FAB, which has, I think, the smooth function. For the spherical, it's yeah. So yeah.
Cool. Other questions or comments? What's next for you?
What's next for me? Keep improving the package and new projects. The one with Francesca is
Okay, so you're gonna
first immediately on my list. Yeah.
just go to a different type of.
Yeah, the software package is there, so I'll
Yep.
look at it from time to time to improve it.
All right, let's thank Lauren again. And who's up? Josh is up. Okay, and we have, yes, symbolic regression. But, okay, I'll. Five when you have five. Or it's like everybody else follows instructions and then you have this.
Is there another collective document? This is the, oh yeah, that's it. Oh, That always helps.
Yeah.
Thank you very much.
Okay, we're ready.
Hi, everybody. My name's Josh. I'm a second year in the department, and it's my second year also on Team VTech. And I'm going to be telling you about an update that we have for symbolic regression in nuclear physics. Just a little brief outline. I'm going to introduce the method because last year Pablo was kind enough to share his slot time with us, and this didn't leave much time for us to get into the nitty-gritty, some of the details that we can discuss about the method, which I'm going to talk to you about today. And then I'm going to tell you about the work that we did in the last year, and then I'm going to tell you about the work moving forward, specifically going into the summer, and then we're going to have a conclusion and outlook for everything that we talked about. Before getting into that, before we start discussing everything, I just wanted to highlight something very quickly. Symbolic regression is a subset of something called genetic programming, which is a subset of some evolutionary algorithms and evolutionary computing. I wanted to highlight specifically that we do have people doing genetic programming in the group. There was a nice paper that was a guide for genetic programming for the many-body problem. But I do symbolic regression. And to start discussing that, we can imagine that we have some kind of desired distribution or function that we are interested in learning how to represent, but we don't know how to do so yet. And we have some relevant features, functions and distributions that we think are relevant to that desired distribution, but we don't have the map. We would like to find that map. Symbolic regression potentially can provide that mapping for us. But to take a step back, I like to think about it as eating cake. So I go to my friend's house, they give me some chocolate cake. I think it's delicious. I ask them, how did you make this cake? I want to make it for myself. And for some odd reason, they only tell me that, oh, I put eggs, sugar, and chocolate into the cake. But they don't tell me the recipe. I would like to use symbolic regression to find that recipe. And to continue with this analogy, we're going to take like a use case look at linear regression analysis. So, when we have data that's in some dimensional space that looks fairly linear, we look at it, we say, I can fit a line to it. We can take what we believe are relevant features, X, and we can multiply them by some coefficient C and throw on a bias term just to be safe. And then we can start tuning those parameters and seeing how it does. In the case that it's a line, it works very well. But if we were to try and apply this to our cake situation, we would have our chocolate, sugar, eggs, and our coefficients that we would tune for, and this bias term, which just says that, if all these coefficients tune to be 0, I should still have some semblance of cake. If I try that though, like what we're kind of doing is just saying maybe we have some proportion of these ingredients and we just kind of pile them all on top of each other. Does that make a good chocolate cake? Probably not. You guys wouldn't want to come to my house and try my chocolate cake. And if we take a look at what's happening, what we basically did was linear regression. So we have our relevant features or ingredients, and we have these tunable coefficients, and we multiply them together, we add them all up and put them there. But we have some idea of how a cake is made, right? When you look at this idea that maybe, you take your chocolate and you melt it by boiling it, you then mix it together with your other ingredients, and you put it in the oven for some amount of time at some temperature, you're going to get a cake out. But this structure does not lend itself to linear regression. And it also has more involved operations going on instead of just multiplying, addition, subtraction, division, all that fun stuff. So the hope is that we can do symbolic regression analysis to try and piece together by taking all these different ingredients and things we can do with those ingredients to form a cake. Let's just continue with this idea that this is like the recipe for a cake. But we don't know this a priori. We don't know how to bake the cake. We're trying to figure out how to bake the cake. So, what ingredient should we put in the cake? I have some semblance of some knowledge of baking. Flour would be pretty good. But, who's to say that there shouldn't be any fish in this cake? Maybe I truly don't know whatever kind of cake you can make. So maybe we should throw that in. Also, how should we prepare these ingredients? When I'm done baking the cake, should I throw it on the grill to get like a nice crust on either side? Or, when we're working with the flour, should we sieve it to like make it smooth? who's to say if we should or shouldn't be doing these things, and should we include them into our analysis? Also, should the cake take 24 hours to bake? If we come up with some kind of recipe and the recipe says, put it in the oven for 24 hours, do we have some kind of way of negotiating whether or not that's a good idea? And finally, how complicated should this recipe be? If it's, this tree diagram doesn't look too bad, but if it becomes insanely long or insanely wide, are we encouraged by that fact? And are we kind of over baking this cake at some point? These points can actually be addressed by the implementation of a loss function and something that I'm going to call complexity quantification. And to discuss these points, we're going to go back to that analogy where we had this linear regression, where we had this equation, and I showed you this tree structure. We can talk about how complex this model is by looking at these nodes, and we assign them the value 1 or whatever you like. We then take a look at every single node, so the coefficients, the features, and the operations, and we add them all up together. So in this case, our model for this linear regression that we did has a complexity of 3, 6, 9, 10, 11. It has about 11 complexity with this kind of scheme. Aside from that, we can implement this loss function, and this can just be viewed as a typical loss function where this was our expression y, and this is the true distribution that we were looking at, and we can take some nth norm to look at the performance of the residual. We can do more fun things by implementing some physical constraints where I've labeled PI as just some set of physics constraints that we want to bake into our model that hopefully helps us converge faster. And these lambdas can be viewed as just weights or coefficients that dictate how strong the response to that constraint is. The package that we've been working with, it works. Sorry, I wasn't sure if this graphic was actually going to work, but I'm glad it did because it looks really cool. The package that we've been working with so far is called PySR. It was written by Miles Cranmer. If you follow this QR code, it'll take you to the paper. This code will take you to the site, and this also links to the GitHub where you can find this really cool graphic and take a look at it. It shows explicitly these details that I've been dancing around of how exactly the models are adjusted in this space that we synthesize from the operation of the features. So that was symbolic regression. I'm going to show you the things that we did to apply it in the last year. We've had some discussions about the charge radii of nuclei. It's a physical observable of interest. Our friends in the lab are fond of measuring it. We like to use it in our own analysis, and it's generally just a good idea to try and get it down right. The way we go about calculating that is by taking something known as a charge density, integrating it against some distance squared over some volume, and you get the square of that value. The charge density can be viewed as the Fourier transform of something known as the charge form factor, where the charge form factor is this nice expression right here. Well, where I will just highlight these G functions, which are known as Sachs form factors, encode information about the electric and magnetic components of your quantities. We also have the nuclear form factor here in red. And finally, in blue, we have something known as the spin orbit form factor. Even when you do all of this, there's still something that you need to do on top of it, which is some center of mass foldings, which is just corrections to ensure that once you do this final calculation, you get a better representation of your system. If we inspect, however, the proton density and the charge density of, say, calcium 40, we see a pretty good likeness. They're not too far off from each other. So a question that we asked within the group was, knowing symbolic regression, is there some way that we can feed the regressor these two densities and kind of learn small corrections? And is there any, how will that perform? And is there any extractable physics that we can get from that? The way we went about doing that was we obtained the nuclear properties of available nuclei. We did this using DFT calculations. We took a selection of nuclei that we wanted to feed into our regressor as the target distribution, the cake, and we linked them sequentially. We specified our loss, and then we just started the algorithm to see what would happen. This is the loss that we worked with. We did some playing around for the form of this loss, but we played with these weights, and we played with the form of these residuals. And this is just the final form that we ended up on. And when we do that, we ended up with a whole host of expressions that we can look at I'm just going to show 4 here explicitly. Along this left column, we have the model. On this farthest right column, we have the loss, which just, again, is the performance of fit metric according to the last expression that we saw. We have the complexity, which was the sum of all those nodes for these expressions that we see. And then we have the expressions themselves. Model D is complexity 26, which is very heavy. We're going to show it to you on the next slide because that's how large it is. But starting here from model A, we see that the proton density and the Laplacian of that quantity were first selected along with some small term on top. This is pretty encouraging to see as like a kind of a low complexity model because the Laplacian encodes information about curvature, the surface of the nucleus. So in terms of like how close of a fit the proton density was to the charge density, you just needed something at the surface to get it right. And the regressor was able to kind of pick that up immediately. Moving upwards in complexity, we see that it drops this noise term and it drops the proton density as well. And we have the emergence of this coefficient come out. So there's further confidence that we see in this Laplacian term surviving. And we took a look at this coefficient, and it's oddly close to the average value of the charge density or the proton density of each nucleus at the origin. So at R is equal to 0, rho C, rho B. You take the average of all those values of the training nuclei. It was pretty close. It was interesting to know. But we go up in complexity once again. The coefficient survives, our Laplacian term survives. And now we have the inclusion of this divergence term, which is the divergence of the spin orbit current. This is also encouraging to see. Oh, excuse me, sorry. This was also encouraging to see because this is the spin orbit current term. When I was showing you the expressions that you do to construct the charge form factor, I highlighted that term in blue. That is the spin orbit form factor. So it was really cool to see that the way that you construct this by doing a lot of really cool physics, the regressor was able to pick up on that as well. There's a contribution there as well. Now, before moving on to the next slide where we'll see 26, I just wanted to highlight, we have the loss here. They're at the same order of magnitude. And to go from complexity 8 at 0.02 to complexity 26, so we've tripled our complexity. We stay at the same order of magnitude. We just basically divide the loss in half. And this is what we get from it. This is Model D, complexity 26 in all of its glory. I'm not going to spend as much time looking at this because there's a lot going on here, but we can see some fun things. The emergence of neutron quantities as well, and the mixture of those with proton quantities. In addition to that, like they're combined in some odd fashion, which is interesting. But something that I was taking a look at that was really interesting was we're basically taking the square root of the proton density squared minus some term and dividing that by this whole expression. This is basically just the proton density. And we see here the Laplacian and the divergence term. So this is model C, and it's either persisted into the higher complexity model, or it originated in this high complexity model and traversed downwards into the low complexity models, so which again adds further confidence into the fact that if it's able to survive like every combination of function, it's a pretty good representation. There's a lot going on at this slide. This is just a table from the last thing for ease of reference, but we have a plot here that we'd like to show you, which is the loss versus complexity, in which case, this is the total collection of models that we have available that were generated by the symbolic regressor. This collection of models is known as a Pareto front. That just basically means we're looking for a set of functions or solutions in this space, which optimizes some quantity, which I'll get to here in a second. The dots with black backgrounds are the models themselves. So this is A, this is B, this is C, this is D. And we see that, D has a pretty good loss. A, in comparison to D, doesn't have great loss. However, we constructed this quantity called score, which is distinct from what Patrick was talking about. Sorry to mix in the different nomenclature. But we took the score to be the Euclidean distance of the loss divided by its mean value and the complexity divided by its mean value. And in doing that, we basically just paint a circle in the background. And the solution to our Pareto front is to say, how far is your model from the origin. The closer you are, the better. And employing that philosophy, we see that B, C, and this middling complexity are, pretty good solutions for that metric. Now we can take a look at the actual performance of the models themselves. I'm not going to show model D anymore. We saw that its loss was pretty good as well, but we took a strong interest in the first three models. So what we did was, these are the same plots essentially. So we have the radius, the distance, not the radius, the distance here on the bottom. This top plot is just the charge density, where we showed the target distribution, the folded density, along with our three models. And just to highlight the performance, because these lines are kind of sitting on top of each other, we took the residual against the folded density at the bottom. And we show this for 48 calcium and oganesson 302. 48 calcium was in our training set. Oganesson was in our validation set, and that's why it's kind of bold. But we see here, it's pretty good performance. For calcium, we're at the -4th order, and for oganesson, we're at the -3rd order. We also wanted to compare the performance for the charge density. So we took the percent error against the folded density, and this is a much nicer plot to see, so you can see way more validation in training nuclei. And there's just some quick things to highlight. Model A seems to be pretty good when it comes to these lighter nuclei up to calcium, it looks like. But when we emerge into nickel in the higher mass nuclei, there seems to be a divergence, which indicates some kind of important interest in those other terms that we saw. Specifically, I think the divergence of the spin orbit plots. But across the board in general, sub 1% discrepancy, not too bad. It's pretty good. That was the work that we did in the last year, and now I'll just quickly talk about the work that we're going to be doing going into the summer and onwards. I actually talked about this last year at STREAMLINE. We're interested. Oh, please forgive the oddity that happened there. But we're interested when you're doing DFT, we do something called density constrained, density functional theory. In which case, we have some idea of what the density should start as. We do some calculations, and we want to end up at a more representative view of this model. And we typically do this through some constraining field, and we do this to get faithful representation of our system. This was what I actually showed at last year's talk. So this was the actual distribution that we had from the calculation, and then this was PySR's attempt at recreating it. It did pretty nice for this outer ring, but as we can see, there's some internal structure that just wasn't captured yet. At the time, we just left it there for now, but now we're coming back to it. And the starting point is basically to look at this iteration scheme. So density functional theory is an iteration scheme, in which case you have updates to these wave functions. In which case, you take your old wave function, you subtract off your Hartree-Fock Hamiltonian, you have some damping operator, and you have that scaled against as an update for your old wave function. And then to preserve orthonormality, you do Gram-Schmidt, Gram-Schmidt orthonormality, and you get an update. So people in this paper pointed out that when you do this, when you have some quantity of interest, Q, you can also think of this as directly the density, so rho. When you do this, the average value is not preserved for the observable, which is not desirable. So they did an update to that, which was just to include this lambda term with Q. And this is just Lagrange multipliers. And you employ this so that you can kind of wrangle the distribution back to preserve this average value between iterations. And when you do that, you need to update this value for lambda as well. And you do some fun calculations on top of that. This just increases the expense of your calculation and adds more complexity into your calculation as well. So our question moving forward is there a way that we can learn this distribution from some selection of nuclei and apply it such that we don't have to do this every single time? And now we can get to the conclusion and outlook. So as we saw, symbolic regression analysis is showing promise to be a powerful tool in the nuclear environment. I didn't really discuss any UQ, but UQ is always fun, so we would like to use certain uncertainty quantification on our generated models. We also want to make a search for more robust methods that we can employ to build more confidence in these generated models. And if you have any ideas that you felt inspired by when seeing me talk about cake, please come and talk to us. We're always open for fun discussion and fun projects, give the time and everybody's free time. I just wanted to highlight as well, I work with really great people and I'm really thankful to be here. Thank you very much for listening. I'll take questions.
Okay, Patrick.
Awesome. So you showed the results on these training nuclei and validation nuclei. You got unstable tests of generalized. The validation you're using is like a stopping condition.
No, sorry, I suppose by validation I mean test.
Okay. That gets that in all machine learning. It's not your fault.
So the validation nuclei was never seen by the training in the regressor. So afterwards, we then threw in some selection of nuclei and see how to do.
Okay.
I'm curious, a couple of the expressions that were found some of the more complicated. Divided by the proton or neutron. But of course, that decays exponentially. Did the symbolic regressor have any numerical issues with dividing by a very small population? Feels like you probably would have seen it obviously if it was just divided by zero.
Yes, through the charge density, no, but I'll take us back to the loss function. And when we were playing for the form of this loss function, we would be doing calculations, and some of the models that we would get would generate a charge radius of 0 for some reason. I don't know, but if you divide by if you divide by that, it's not good.
Yeah, so on this slide, it seems to me like model B is actually, like, just from my naive eye, model B looks less complex than model A. And I see there's like an asterisk next to complexity 6. Are those two things related?
Thank you for asking. I forgot to mention. There is a discrepancy in the reported complexity, and these asterisks are meant to denote that. The regressor is very good at making simplifications on the level of the features that you pass. So if you have feature X and then feature X times Y, and you have a function that's YX divided by X, in that case, it can't actually select out that division by X. It cannot resolve that to unity. But if it constructs Y times X divided by X, it will resolve that. So sometimes there's redundancy in these models. And so for these lower complexity ones, I took the liberty of simplifying that. But we even saw that here in model D land. There were some instances where the regressor couldn't pick that up. That here as well. It doesn't know what rho p is. It knows what rho p squared is, and it took the square root of that. So it's essentially saying do rho p, but I was lazy and didn't want to remove it.
Yeah, and then as a follow-up, if you'll indulge me, so you eventually calculate a score by the Euclidean distance of the complexity and the like the error. Has there been any thought to changing that error model so that you can have like some sort of like quote unquote effective complexity? Because for example, in that plot, it shows that like model B is more quote unquote complex than model A. But if it is more like symbolically simple, it seems like it just generically outperforms model A.
That is a very good point. That has not been an area of exploration, but we should talk about it.
So I think I have Pablo and then Mark.
That was going to be my question, but then based
Okay,
on
you're
this
done.
discussion, but based on this discussion, I have a suggestion. I think definitely whenever you make the Pareto prompt, you shouldn't use the complexity that the regressor normally thinks. But if you have anything like Wolfram or any symbolic manipulation, or you yourself when you're doing that, I think it would make more sense that you use that simplified complexity And you can think it that in the moment that the algorithm is searching for equations, you will have some kind of heuristic of complexity. But at the moment of actually making the decision, you adjust that heuristic to match the reality.
You put it through a tokenizer like an LLMC. So that's a very good measure of complexity of expressions sometimes.
To go on the model D slide, I guess the first thing I noticed was that there's a condensate term that's on the last term. But
Oh, here.
yeah, on the list. That you can divide out the neutron row on the right side, I guess. It's also take out the order of operations. Or actually, not that one side. Anyway, how do you like? Can you apply almost like a correction afterwards that you correct these terms and then retest the complexity and loss and then I guess on it's a naive question, but like I guess how do you kind of think about like the correction as
Oh, like, how do we say that, oh, this term is redundant, get rid of it?
yeah, I guess like I guess for example on the neutron row, if you're kind of that could be a very valid like density form or not or like a form that isn't a function. But let's say you have a 1 over row into a third. How do you know that like okay this is not going on to do that thing?
Sorry, I'll have to talk with you more about it. I'm not on the same.
I think the other is it is the machine that's going off and doing jump for this high complexity. You're creating noise instead of fun.
True, but like my question is, I can say that this thing is fitting drama. It's putting a lot of redundant parts. Yeah, but then
It's on this point.
as correction, you
This
take
is
out the,
coming back to Daniel's question.
how do you kind of judge like, okay, that is a redundant term.
It's high complexity, so you just ignore this full expression.
Okay.
Josh shows it to impress us with his powers of symbolic regression.
So Daniel, you asked this question about what happens when goes, nothing happens. And you can see it here, because you have a row n to the power of 4 in the denominator, then you have row n in the numerator, and in the front of everything is row n, and you have divergence of j over rho n in the same power.
Yes, I see it now.
Everything is good.
So let me just finish with the more physics motivated one. Did you try this in momentum space?
No, just everything that you saw is the.
You might want to analyzing densities and things tells you a lot in momentum.
But look at the momentum correction here.
But looking at momentum, you could see like differences. You could see there's a clear wavelength, for example, which tells you should really look at something. Okay, let's thank everybody again.
So, yeah, let me make a few announcements.